at at 6:20 yesterday morning. You hopefully would have seen this, the launch of the DART mission. I've muted the sound, by the way, because sometimes sound doesn't work so well over Zoom, but can you just confirm you're seeing the video?
Yeah, no, it's perfect, Alan. It's great.
Super, thank you. Well, this was liftoff yesterday from Vandenberg US Air Force Base over in California. I wasn't there, as you can see, because I'm here today, but I had a bunch of friends that did manage to fly over to watch it. And importantly, not only did we get to see the launch, but 55 minutes later, we saw DART ejected from the second stage booster once that booster had aligned itself and pushed both components onto the required trajectory. And so DART is now out there, and I can tell you right now that all systems are nominal. Solar cells are fine, and the instruments are starting to undergo checkout, warming up, and so on. It will take a little while to get the spacecraft fully operational, but we fully expect at our next team meeting, which will be next month, to be looking at the first images from the onboard camera and the initial assessment of their quality. So that's where we are now with the spacecraft flying. Why is DART flying at all? Let's go and take a quick look at this simple graphic of our solar system, where the planets and the sun are to scale, but not, of course, the distances between them. And if you pick up any introductory astronomy book of recent years, at least, this is a kind of diagram you might see, where you have the sun to the left. Oops, sorry about this, excuse me. We have the inner planets, Mercury through to Mars. We have the outer gas giant and ice giant planets, Jupiter, Saturn, Uranus, and Neptune. And then generally indicated somehow are the other smaller objects orbiting the sun, the dwarf planets, the asteroids, and the comets. And the vast majority of them lie between Mars and Jupiter in the asteroid belt and beyond Neptune in the Kuiper belt. But we know, and we've known for over 100 years, that not all the smaller bodies stay within those regions. Some have orbits that cross those of the planets, particularly the Earth. And one way we know this is because, well, we've already heard from Paul earlier that we're going to get a meteor shower, the Geminid meteor shower next month, one of the three impressive or dependable meteor showers, should I say, every year. And that actually is ejected from an asteroid unusually. Most meteor showers come from comets, but the Geminids come from the asteroid 3200 Phaethon, which is a small near-Earth asteroid in that its orbit crosses that of our planet, and we are seeing fragments from that asteroid every December the 13th enter our atmosphere. Every so often, we see something brighter than a meteor or a shooting star. We see a fireball. And on this plot, we've got the most energetic fireballs detected in our atmosphere from US Department of Defense satellites since 1988 up until, well, last week, when the last one was detected on November the 17th. And you can see that the Earth is regularly peppered by objects smaller than those objects that create meteors. Meteors are created by dust grains, perhaps a millimeter across. Fireballs, you would have anything from a pea-sized object to a stone-sized object, perhaps even basketball-sized object, or larger. These we see as fireballs in the upper atmosphere, and they're spectacular to see if you ever see one. I saw one myself about a month ago. But again, these are no real concern to us. The rocks that cause these fireballs when they enter our atmosphere harmlessly burn up at rather high altitude. But the larger an object is, the lower down in our atmosphere it can penetrate. And the most recent classic example of this, of course, was over the Russian city of Chelyabinsk 8 years ago, when an 18-meter small asteroid entered the atmosphere without warning and exploded at an altitude of just over 20 kilometers in the atmosphere. Now, again, our atmosphere prevented most of it from reaching the ground, but the shock wave from that explosion shattered windows, collapsed walls, and caused 1,600 injuries in the nearby city. If we go up in size from 18 meters, at the beginning of the last century, we had the Tunguska impact in Siberia. Again, Russia, it's not anything the cosmos has against Russians. It's simply Russia is a very, very, very big country, bigger than it would normally appear on maps of the world because of distortion. And on the 30th of June, 1908, we had we believe something like a 50-meter diameter small asteroid enter the atmosphere. It didn't explode until it reached 5 or 6 kilometers altitude, and this resulting blast wave wiped out 2,000 kilometers square of forest. If that had happened a few hours later over Paris or Berlin or London, then the history of Europe would have been very, very different in the last century, because those cities wouldn't exist anymore. So that's why every year we celebrate Asteroid Day on the 30th of June in memory of the Tunguska impact. Now, if we go back to even larger sizes, or we go to even larger sizes, we can go back further in time and we can go and visit a place like this, Meteor Crater in Arizona. Now, amazingly, this 1 mile diameter crater, it was made from something rather the same size as the Tunguska impactor. But instead of being made from a relatively porous, fragile, rocky small asteroid, or perhaps even a cometary body, as some have speculated, this object was a rather dense solid iron nickel asteroid. And one can see the tremendous effects 49,000 years after that impact. Now, this is an image I took, or this is a picture I took last time I was there about 8 years ago. I should have been there last year, but we had other things going on in the world, unfortunately, which stopped travel. But I do have another image just to put everything into context, into scale, which is a picture I took of, I think this was the west wall, the northwest wall of the crater. And you can see the geology exposed there, plus all the slumping of the rock going into the crater. And if you look very carefully, you might see a bunch of my colleagues that are walking into the crater at that point. And if you can't see them on this slide, I'll just bring them up. And if you zoom up, hopefully you can now see my colleagues who happen to be, of course, specialists in near-Earth asteroids going into the crater. And it's one of those cases where you hope that lightning isn't going to strike twice, because there'd be a lot of knowledge lost if we had 2 impacts in the same place on that particular date. So, of course, we have a number of craters now mapped around the world. Here we've got a recent map of them done a few years ago. And the big impact that everybody knows about, of course, is over here in the Gulf of Mexico, just south of the United States of America, where 66 million years ago, a 10-kilometer diameter asteroid hit the Earth and proceeded to wipe out the dinosaurs, which is a shame for the dinosaurs, but hooray for us mammals, because we're now the dominant species. So we are the dominant species. We'd rather not go the way of the dinosaurs. And this is why, over the past few decades, astronomers and other scientists and engineers have taken a particular interest in these near-Earth objects, comets and asteroids that come near the Earth and may one day hit us. So we now have a new field of science, planetary defense. And planetary defense, you can read papers and even books on it, but effectively, planetary defense has 3 main tasks. Find them. Find the asteroids and comets that can pass close to our planet. Measure their orbits and find out if they're coming close to us in the next, say, 100 years or so. Second thing is to measure their properties, because by measuring the properties, we can try to calculate what the effect would be of a particular asteroid or comet hitting the Earth in the future. And then, of course, if we, in our cataloguing of the near-Earth asteroids and comets, we find an object that will hit us, and if knowing its properties, we know it would cause significant damage at the surface of the Earth upon impact, we should be prepared to mitigate that impact. And mitigation might be all the way from just civil defense, which is evacuation of the impact area once we know where it is going to hit, all the way through to, of course, deflecting that asteroid or comet to make sure it doesn't hit us. And this is what puts asteroid and comet impacts in a separate category from all other natural disasters. Whether or not we're considering a hurricane or a volcanic eruption or an earthquake, or even people speculated a solar flare, we may be able to predict them to some degree, but we can't stop them or prevent them. An asteroid impact is at the moment the only thing we believe we have the technology to actually avoid happening entirely, by moving that asteroid onto a different orbit so it does not hit the Earth in the future. Well, let's just remind ourselves of those three tasks before we get on to the space missions. We've got to find these objects, first of all, and every night we have a suite of telescopes, mostly at the moment funded by the US, but finally Europe is getting in on the act. And every night they find new objects. And so here's one found today. We've got a small piece of the sky here. This is actually part of the northern sky, and marked in a cross, we see a small dot of light. If we, the Atlas Near-Earth Object Survey took 4 images in the space of 45 minutes. And if you stream them together, one can see that object is moving. And this was discovered but reported by us at about 10:30 this morning. It's probably about 50 meters across, so it's likely to be somewhere around Tunguska size. Now, it looks like it's not going to hit us this time, although we're still not quite sure of the orbit yet. We've known about this object for less than a day, but at the moment it's looking like the close approach would probably be about 25 times further than the moon, so 25 lunar distances. And it looks like the minimum orbit intersection distance, the closest its orbit passes to the Earth's orbit at the moment, is 0.06 astronomical units, which is 0.06 times the distance between the Earth and the Sun. So we're actually quite safe for this thing at the moment, but we've still got to confirm this orbit and tie it down. We're not even exactly sure when the close approach is going to be yet, but it looks like it's going to be in a week or two. We'll know more literally by tomorrow when we've got more observations of this object. So this process of finding near-Earth objects, near-Earth asteroids and near-Earth comets continues all the time. And just to give you an idea of how crowded space can appear, if you depending on how you plot it, here's a sample plot from the IAU Minor Planet Center on a particular date, where we have the sun in the center, the orbits of the planets marked in blue. So we're going out with Mercury, Venus, Earth, and then Mars. Then every green dot on this plot is the position of an asteroid from the main asteroid belt, and the red dots and red markers all show asteroids that we classify as near-Earth asteroids. These are asteroids that pass within the orbit of Mars. And indeed, on a plot like this, it seems like a surprise. We don't have asteroids running into us every day, but remember that space is still big, even in the inner solar system, and you can only make the dots or the symbols on the plot so small before you can't see them anymore. So in fact, one knows that we are not hit that often by asteroids and comets, because if we were, we'd see them ourselves. We would have witnessed one ourselves. But there are a number out there. And importantly, these are just the ones we have catalogued. We have not catalogued all of them to any large degree. We certainly have catalogued almost all of the large dinosaur killer or global climate change objects 1 kilometer across in diameter or larger. But when we get below a kilometer in diameter roughly, then we are still finding new ones all the time. And when we get down to a few hundred meters across, still much larger than the Tunguska and Meteor crater impactors, we have barely scratched the surface of all the asteroids there are out there. So let's just cheer ourselves up. The number of near-Earth asteroids discovered by today, yes, I checked this number just a couple of hours ago, 27,659. And on average, we discover a few more every 24-hour period now with our telescope surveys. The number of near-Earth objects discovered on an impact trajectory and have actually hit us so far have been 4. The first example of that occurred back in 2008. There's been another 3 small asteroid impacts since then where we saw the asteroid before it hit us. And all of those were small asteroids, 4, 5, or 6 meters across. So they all burned up and exploded harmlessly in the upper atmosphere. But it's still good to see that our surveillance system is working at the moment. Remind you then, the second task of planetary defense is to actually measure their properties. And we do a lot of this using ground-based and space-based telescopes. But of course, spectacularly, we now have missions to near-Earth asteroids. And here's 2 beautiful recent examples. On the left, we have the 865-meter diameter near-Earth asteroid Ryugu, visited by the Japanese Hayabusa 2 mission, which went into orbit, sampled its surface, dumped a couple of probes, or actually 3, I think it was 3 surface science packages on the surface, and has now since returned to the Earth with samples of that asteroid. On the right, we have the roughly 500-meter diameter Bennu, visited by the NASA spacecraft OSIRIS-REx, which has also carried out sampling, and that is still en route to us with its samples, and I believe they will get back to us in just over a year's time. So we've learned a lot about near-Earth asteroids, and we have learned a lot about finding them, and we are finding more of them every day. And so that's 2 of the 3 tasks of planetary science in planetary defense. But the third task is something we haven't done as of yet. We haven't tried to mitigate an asteroid impact. And importantly, we should be able to do that because asteroids are nature's way of asking, how's that space program coming along? The dinosaurs didn't have one, and more fool them. We do have one. And so in theory, at least in terms of theoretical technology, we should be able to change the orbit of an asteroid so it doesn't hit us in the future. Now, there are 3 primary technologies that we have looked at over the years, and I've listed all 3 here. On the left, we have the wonderfully titled gravity tractor, and this would use a large spacecraft that would hover at a set distance from a small asteroid. With current technology, we couldn't really do this at anything over probably above 50 or 100 meters across. And over time, a year or a few years, perhaps a decade, as long as we keep firing the thrusters to maintain the distance, just as the gravity of the asteroid is pulling on the spacecraft, the gravity of the spacecraft is pulling on the asteroid, and we can therefore slowly pull the asteroid onto a new orbit around the sun, simply through the gravitational attraction of our spacecraft. But although that works in theory, we don't quite have the technology yet to attempt that, but perhaps we might test that in the next 10 or 20 years. The middle the asteroid deflection technique is the kinetic impactor. And this is where effectively we play cosmic snooker. We take our spacecraft and throw it into the asteroid. And just as a cue ball hits a snooker ball and makes that snooker ball move, the spacecraft hitting the asteroid will make that asteroid change its velocity very slightly and therefore again change its orbit about the sun. Now, finally, we have blast deflection. Now, this is really almost going into Bruce Willis and Armageddon territory, except they got it wrong. Well, they got many things wrong in that movie, except the soundtrack, which was fantastic. There we would take a small nuclear device and explode it off the surface, above the surface of the asteroid. And what that does is vaporize the surface of the asteroid directly below the blast, and the ejector or the vaporized asteroid would go one way, and the main bulk of the surviving asteroid would move slowly the other way, again changing its velocity and changing its path around the sun. So out of these three techniques, the gravity tractor is still probably a little bit away in terms of testing that technology. Blast deflection has its own geopolitical problems, such as launching a nuclear device into space and therefore breaking the 1967 treaty on the peaceful use of space. So we're left with the kinetic impactor, and that's not a bad thing. If we look at this plot, we can basically see, well, if we wanted to deflect an asteroid again, and stop it hitting the Earth at some point in the future, how big an asteroid could we deflect depending on how much warning time we've got? I.e., we detect an asteroid with our telescopes and we say we can figure out it's probably going to hit us in so many years' time. What technology can we use Well, it depends on the size. To be honest, if it's smaller than 50 meters, the likelihood is that we won't know the orbit that well, and it's probable that we won't get the money to launch a deflection mission. So we're left with civil defense, which is effectively evacuating the impact area once we know exactly where it is going to hit. If we go between about 100 and say 100 meters and 500 meters, half a kilometer, the kinetic impactor should work there. And in fact, if we have a long warning time, we should also be able to use a gravity tractor if we can design our spacecraft to pull on that asteroid for several years. Anything going up to several over half a kilometer and above, it's likely that we might have to use blast deflection. So so we have all these techniques. Now the question is, what size is the next impactor that we have to worry about most likely to be? Well, we're most likely to be hit by the very small objects, in fact, so small that we have trouble tracking them at the moment. So we're not going to have any warning time. The larger asteroids, we have mostly all discovered and checked they're not going to hit us in the next century or more. So that leaves us with this region here between about 100 meters and say 300 or 400 meters, in the region where a kinetic impactor should be able to do the job, at least on paper. And so that's the technology that we're going to test. And we're doing this as part of an international collaboration and project we call overall the ADA project, for Asteroid Impact and Deflection Assessment. And it's composed of two spacecraft. The DART mission on the left, which of course launched successfully yesterday, and we reached the target asteroid next September. And the Hera mission, which will launch now in 2024 and reach the target asteroid in 2026. Just to point out that this has been a long time coming. On the top left, I've got a picture from one of our first meetings with the European Space Agency in 2004. In fact, I was in a meeting a couple of years before that. But at about the same time as the meetings in the US, meetings were also going on in Europe set up by the space agencies with interested scientists and engineers to work out what could we do to mitigate an asteroid impact. Now, in the intervening years, we had at least one proposal to the space agencies, which unfortunately was not accepted and was not funded, but we keep pushing. And by the time of the ADA meeting in Nice in 2016, the DART mission from NASA had been approved. But unfortunately, that year, the European side of the mission was not approved. And so at that point, DART was flying by itself. But we continued pushing in Europe, in particular, going through 2017, 2018. Here we've got all of us standing underneath a dinosaur skeleton in Berlin that year. And then the second time around, we got our mission approved last year not last year, 2 years ago in Madrid. So I try to forget the year 2020 like a lot of us do. It wasn't great for doing a lot of things. But yeah, so we finally got it approved in 2019. So the target we have for our missions is the asteroid 65803 Didymos. And here we've got a little animation showing the orbit of Didymos going around the sun, along with the inner planets. You can see that it gets quite close to the Earth's orbit, but then at the other end of its orbit, it's out beyond the orbit of Mars and actually is flying through the inner edge of the asteroid belt. And the important thing is that therefore this asteroid comes regularly, approaches the Earth, although its closest approach is just outside the Earth's orbit, so it can't actually hit us at the moment in its orbital evolution. Importantly, the last time it was very close to us in 2003, it was observed by radar telescopes, and in particular the unfortunately now deceased Arecibo radar telescope down in Puerto Rico. And here's radar images from November the 23rd in 2003. And one can see the reflections the radar reflections from Didymos, but also in each of these images, one can see a little dot of light that seems to be in fact moving relative to Didymos. These were the images that showed us that Didymos has a moon that we now call Dimorphos. Now, from these images, it's a little difficult radar images are very difficult to interpret. They're not really the same as photographic images. But luckily for us, we also had another technique of observing this moon. And here we can see light curves of the asteroid, the changes in brightness as a function of time back in 2003, obtained by a very great expert in this field, Peter Pravec from the Czech Republic. And here we can see that it seems to be rather complicated, but that's because what we have is the fast spin of Didymos itself, and it spins once every 2.25 hours. And then beyond that, we have these eclipses where the moon is passing in front of or behind the main asteroid. So we've got these two techniques of studying this moon, Dimorphos. And using these, we actually have a very, very good picture of Didymos and Dimorphos, although we should state that the only time we've seen them as anything other than a single point of light is with the radar images in 2003. So here I've used other asteroid images as a mock-up of what they may look like. We have Didymos itself, which is 780 meters across. Then we also have its moon Dimorphos, which is approximately 160 meters across. And the orbital distance between them, between their centers of mass, is 1.2 kilometers. So this is a rather compact binary asteroid system with Dimorphos orbiting Didymos. Now, to put this into context, this is the Connemara Astronomy Society. So here we've got an overhead view of Galway, courtesy of Google Earth. And on this, I can drop the Didymos system. There we go. If they actually fell on Galway, it would be much more spectacular than that. But as I said, that can't happen at the moment, you'd be glad to know. So as you can see, the system itself, it's about 1.2 kilometers across. So it would comfortably cover the center of Galway. Now, if we look at the orbit, then the moon, Dimorphos, orbits Didymos once every 11.92 hours, or once every 11 hours 55 minutes. Didymos itself is spinning once every 2.26 hours. We don't know how fast Dimorphos, the moon, is spinning. We expect it to be close to the orbital period of 11.92 hours because of the tidal force between Didymos and the moon. Just as the tidal force between the Earth and our moon has synchronized our moon's rotation to its orbit, so we only see one face of our moon from Earth. So we think from Didymos, you would only ever see one face of Dimorphos, but we don't have any evidence for that. It's just a theoretical prediction. Okay. One other thing that I've been careful to put on the right way around here, both Didymos and the orbit, the Didymos' spin and the orbit of Dimorphos is split 180 degrees to the normal way that things spin for the planets in the solar system. So they're spinning retrograde and orbiting retrograde relative to the Earth's orbit. So what's going there? DART is going there now, and it's, as we know, it's over a day and a half into its journey. So this is a schematic of the Double Asteroid Redirection Test spacecraft, to give DART its full title. And in terms of interplanetary spacecraft, it's relatively simple, as simple as any interplanetary spacecraft can be. It's, of course, got these fantastic rollout solar arrays, the ROSA arrays, which now that they've successfully been tested on the International Space Station and now successfully working on DART, will hopefully be used for future interplanetary missions, at least in the inner solar system. Then we have an engine on board, and that's the iron engine, the NEXT-C engine, which is the engine that will primarily guide DART to its impact with the Didymos system. And then the only real instrument then on board, and this is what makes it so simple for an interplanetary spacecraft, is the camera. The Draco camera, which is based on the camera that flew on New Horizons, the Pluto flyby spacecraft, which returned such spectacular images of Pluto back in 2015. Now, there is one other thing on board, apart from the iron engine and the camera, which I'll come to in a minute, which is another smaller spacecraft called LICIA-Q, but I'll come to that in a minute. So here's how DART is going to work. We have the Earth and Didymos here in their mutual orbits. And then here we have the DART launch. And you can see that DART's remains pretty close to Earth during the next 10 months. And that's because it only has to travel very distant slightly from the sun to reach Didymos in September, late September next year. And that's when it's going to impact. But of course, it's not going to impact the main asteroid Didymos. It will impact the moon, Dimorphos. And here's the plan. DART will hit Dimorphos as a kinetic impactor, and in being destroyed, change its orbital velocity, but not the orbital velocity of an asteroid around the sun. Rather, this is going to be the change of velocity of an asteroid moon around its parent asteroid. And this is beautiful for a number of reasons. First of all, Dimorphos, 160 meters across, is almost precisely the size, or really is pretty much the size we would pick for a test of a kinetic impact mission. Can we change the orbit of a small asteroid? Secondly, because Dimorphos is in orbit about Didymos, then when it changes its velocity, the orbit will change, and we'll be able to see that change in orbit using telescopes on Earth. And it should change by about 10 minutes or more. So instead of having an 11-hour, 55-minute period orbit, that orbital period should go down to 11 hours, 45 minutes, or even shorter. Third, because we're only changing the energy, the orbital energy of Dimorphos, not Didymos, the actual orbit of this system around the sun will effectively not be changed. And so it is perfectly safe to carry out this test. We cannot change the orbit of the Didymos-Dimorphos system so that it ends up on an impact trajectory with the Earth. And that's really important because this is an American mission and America has lots of lawyers. So just point that out. So what's DART going to see? Well, apart from the camera testing and so on, for most of the next 10 months, it's not going to see anything. In fact, it's only going to start observing Didymos a few weeks before impact. And here's, in fact, the timeline of the last hour of life of the DART spacecraft. 1 hour before impact, it will be 24,000 kilometers from the Didymos system. Didymos will be just about resolved in the camera. Dimorphos won't, but 1 hour before impact, we will start being able to pick out Dimorphos from Didymos. Before then, they're a single point of light as they indeed appear to telescopes on Earth. 4 minutes from the encounter, we'll have our final divert maneuver corrections using the autonomous onboard software. And as you can see by this stage, we've got very clear images of both of Didymos and Dimorphos. 2 minutes to impact, there are no more changes that will be done, and Dimorphos is growing in size. Then 20 seconds before impact, Dimorphos will be overfilling the frame. And in fact, this is probably one of the last images we will get from the spacecraft. We're hoping for one more within the last 20 seconds before impact. But remember that DART will be approaching this asteroid to hit it at over 6 kilometers per second. So you don't have much time to take the images, process them, and send them back to Earth. Because in 20 seconds after this image, the spacecraft doesn't exist anymore. But we'd still like to see or get some idea of what was happening. Because if this was all that there was, as soon as DART hits Dimorphos, all we've got left with are the telescopes on Earth. And no matter how impressive they are, it's going to be very difficult to see the details of that impact. So DART is carrying a small CubeSat, Licia Cube, from the Italian Space Agency. And this will be launched about a week to 10 days before impact. And its job is simply to provide at least 3 images of the impact plume, the ejector, from the DART impact 3 minutes after DART has hit Dimorphos. So this is it. It's in fact literally is about the size of a small suitcase. It's actually based on a couple of other CubeSats, or one of the other CubeSats that will be launched. I think it's next year, and I'm sure Paul or Terry or somebody more knowledgeable about this will correct me, when the first test mission of the Space Launch System is launched to the moon. It's gonna that mission will have a number of secondary spacecraft that it releases on the way, including a couple of CubeSats that will be going to orbit around the moon. So it's going to give us close-up images of the impact and what happens, although we'll only be doing that for a few minutes after impact. And then because DART won't exist anymore, Dimorphos will be sending those images directly back to Earth, But because of its small size and low power of the transmitter, that's going to take a few weeks to get back. Now, once DART has done its business, we will have moved an asteroid. And if things were simple, as they sometimes are in my physics lectures, although sometimes not, sorry, Sinead, then this would be a simple application of something discovered by Newton, the conservation of momentum. Or was it Galileo? I can't remember that far back now. The momentum of an object is its mass times velocity, how its speed, how fast it's traveling. And in a very simple collision between two objects, that quantity is conserved. So if we have the asteroid here and DART approaching, we know the mass of DART, we know its velocity, and those two numbers combined give us something called its momentum. And then that momentum would be passed onto Dimorphos. So depending on how large its mass was, that would tell us how much or with what extra velocity Dimorphos was moved. However, asteroids are not simple, and they have there's a number of unknowns about asteroid structures and how they respond to impact. And the biggest one is that when DART forms a crater on Dimorphos, it will kick up ejecta, bits of asteroid that will be thrown out in the opposite direction. And that ejecta has its own momentum. So in fact, we believe the asteroid will move more than just from the spacecraft alone. It will move from the momentum given to it by the impact of DART, but then added on to that will be the momentum given to it by all these rocks from the surface being thrown out one way, moving the asteroid even faster in the other direction. And that's where one of the main uncertainties lies. We do not know how effective Dimorphos, or how effective the DART impact with Dimorphos will be. And we could do all kinds of simulations, but basically we quantify it in terms of a number we call beta in impact physics and planetary defense. If beta is 1, then the only extra momentum given to Dimorphos is the momentum of the DART spacecraft. And we get a small increase in momentum, which is a small increase in velocity. If beta is 2, if we get twice as much momentum, because of rocks being thrown in the opposite direction from the DART impact, then we get a bigger increase in momentum and a bigger change in velocity. If beta is 4, which some simulations say could exist with some particular asteroid structures, then we could have a very large momentum increase. And we simply don't know where in this range of values beta will be. We can carry out laboratory simulations, as you can see here on the left, and we can carry out theoretical simulations, as you see here on the right. But the range of results we get and expect are so large, the only way to know how effective a kinetic impactor is to do the test. Now, DART will move the asteroid. There's no doubt, we have no doubt about that. But the effect of beta that we need to calculate the effectiveness, this beta factor, we need to know the mass of Dimorphos, and we won't get that to any great degree of accuracy with DART and LISA-Cube. So he'll give you another example. Here's 3 models. Here's now 3 theoretical models, depending on whether or not we've got solid rock on the left, we've got rock with lots of little cracks and holes in it in the middle, or we've got something possibly closer to what we expect Dimorphos to be. It's just a rubble pile, just a bunch of rocks held together by weak cohesive forces and self-gravity. And here we can see beta values ranging from 1.14 to 1.32 to 1.55, with a corresponding change in velocity of Dimorphos, ranging from 1.75 centimeters per second up to 2.5 centimeters per second in orbital velocity. And we simply don't know how effective, therefore, a kinetic impactor will be. To really know that, we need to make better measurements, and that's where the follow-up mission comes in, Hera. Hera will launch in 2024. It will arrive right at the end of 2026, and depending on your definition of arrival, because it will slow down and approach quite carefully Didymos and Dimorphos, because it's a rendezvous mission, not a flyby or impact mission, then it's arriving about Christmas time, New Year 2026, assuming we launch on time in October 2024. Now, Hera is a much more complicated spacecraft. It's got a number of different instruments on board, a camera, a laser rangefinder to accurately measure its distances to the asteroids and also help with their shape determination. It's going to have an infrared imager and also another spectrograph. It's going to have radio sites for measuring masses. And it's also, like DART, going to be carrying CubeSats. Here's the trajectory it will take. And remember now, this is a rendezvous mission, so it's got to match orbits with Didymos and Dimorphos. It will launch in October 2024 here, and it will take 2.5 years to match orbits. It will do 1 Mars flyby as it goes out, and then when it comes back in, it will rendezvous with Didymos and Dimorphos around about here. Once it gets there, where we're still planning the actual trajectory we'll do, it will not go into orbit around Didymos and Dimorphos. It's really going to be kind of flying alongside them, if you like. And in fact, we'll do something that we did with the Rosetta spacecraft at Comet 67P, Churyumov-Gerasimenko. If Paul can say it, so can I. And depending on which observation phase where the spacecraft is in, we'll either be doing very long, slow loops with 3 or 4 days between paths as we just kind of go around in a rectangle around Didymos and Dimorphos over here when we're doing the early characterization phase after we've just arrived at the system. Or if you look ahead towards 6 months down the line, when we're very much closer in and doing the detailed characterization phase, what we do with these much closer flyby arcs, in fact, going within 5 kilometers of the asteroids and making very, very detailed measurements. And we need to spend our time doing this because, as I said, the important thing that Hera is going to do, it's going to measure the mass of Dimorphos. It's going to measure the mass of the moon. And it's not going to do that by flying very close to the moon and measuring its gravity that way. What it's going to do is, first of all, it's going to have its own onboard navigation. And again, this will be like DART's navigation when it's moving towards impact. This will all be autonomous. It will detect boulders and asteroids on the surfaces and track them and know where it's going and so on. But when we look at, we take the images, we'll measure the mass of the moon by measuring the wobble of Didymos itself, because just as the center of the Earth-Moon system isn't at the center of the Earth, but it's actually a fair way out towards the Earth's crust. Similarly, with Didymos and Dimorphos, we'll be measuring where that center of mass is, and because we know the mass of Didymos, we'll be able to measure the mass of Dimorphos, and therefore know exactly how much mass DART has pushed. But also we're doing other fun things as well, because we believe now, after some further studies, that the impact of DART may well set up some oscillations in the orientation of the moon Dimorphos, and we've been measuring those as well as many other characteristics of the system with Hera. And in particular, we'll be measuring the properties of the impact point and the moon Dimorphos, because we want to be able to put all of these measurements together so that next time we try to use a kinetic impactor on an asteroid may be the time we need to deflect it. And the more knowledge we have about how a kinetic impactor works with the small asteroid, the better. It will also, by the way, just point out, Hera will have its own, as I said, its own 2 CubeSats itself. We have the Juventus CubeSat, which is primarily designed to perform radar observations of Dimorphos and a little bit of Didymos as well. But it would be the first radar mapping, internal radar mapping of a small asteroid by a spacecraft. The Milani CubeSat, the second CubeSat that Hera is carrying, contains a whole bunch of instruments, including additional cameras and spectral imagers to help us assess exactly what type of rock these asteroids are made of. And then we can put that into our models and adjust them when we want to use them for different asteroids. And overall, this slide, I think, pretty much shows what the ADA project comprised of DART and Hera is going to do. We're going to show we can change the orbit of a small asteroid and then measure the effectiveness of that technique, the kinetic impact, and apply that result to other asteroids. And all of this requires precision impact parameters, properties of the crater and the target, and then we can feed that into our calculations should we unfortunately need to move an asteroid for real in the next few decades. So I'll leave you with a little movie showing the entire project. So here we have DART on its way. Thankfully, I can still show this movie because the launch was successful yesterday. And as I said, it will enter the Didymos Dimorphos system in late September next year, traveling at 6 kilometers per second, or relative to the main system. In fact, it's going to hit on the forward face of Dimorphos, so which will mean that we get an extra few hundred meters per second impact velocity. And then 4 years later, Hera will arrive in the system to do that full-blown characterization. So this is a really exciting time for us in planetary defense. The telescope surveys are going well, the physical studies are going well, and now finally we're going to test for the first time our ability to stop an asteroid hitting should one be discovered on an impact trajectory. So I'll just let this small animation play out a little bit more, but I think I'll finish here and just point out that these are the DART and Hera missions. They're coming to an asteroid near you. Thank you.